Right, welcome calculus students. So we're going to skip section 5.3 for now, which is on inverse functions, and jump right into section 5.4, which is exponential functions, both differentiation and integration. Okay, so a exponential function with base e is really what we're looking at. So let's say I've got the function y is equal to e to the x. Now we plotted this out before, and we know that this is the inverse of the natural log graph. And these points here are pretty easy to pick out because whatever value of x you put in, then the y value is going to be e to the x. So if I put in my point x equals 0, then y is going to be equal to e to the 0, which is 1. If I put in 1 for x, then it's going to be y is going to be equal to e to the 1. If I put in 2, it's e to the 2. And if I go backwards, then I get these negative exponents. Now the key thing here is that the domain of exponential functions is all real numbers. However, the range of e to the x, or really e to the u, is open interval from 0 to infinity. So this graph, although it has a horizontal asymptote as in the limit as x goes to negative infinity, so the limit as x goes to negative infinity of e to the x is equal to 0. The function itself can never be equal to 0. And this is important when we're finding critical points and inflection points, as we'll see later. Okay, now in order to find a rule for the derivative of these types of functions, I'll rewrite the function. So I've got y is equal to e to the x. Okay, well, remember that when in section 5.1, when we covered the natural log differentiation technique, is that whenever you have an exponent that's a variable, we can use that natural log differentiation technique. And we're going to use that exact same technique with this particular function. So the first step in trying to find the derivative of y is I'm going to take the natural log of both sides. So natural log of y is equal to the natural log of e to the x. And then I'm going to use the rules of natural log, and I can bring this x out front. And if I do that, then I get the natural log of y is equal to x times the natural log of e. Well, we know that the natural log of e is 1. So I just get natural log of y is equal to x. So now if I differentiate both sides with respect to x, because I'm looking at looking for y prime, which is the derivative of y equals e to the x, then the derivative of the natural log of y using implicit differentiation is 1 over y dy dx, and that's equal to the derivative of x is just 1. So what I'm going to do here is now I'm going to multiply both sides by y. So I get dy dx is just equal to y. And remember that the last step for natural log differentiation technique is to put my y value back in. So I've got dy dx is equal to y, and y originally was e to the x. So this is actually a really interesting differentiation rule, because if I differentiate e to the x, then the derivative of e to the x is just e to the x. And e to the x is the only function where the derivative is the same as the function. And so this is a pretty cool result, I think, because if I go up here, the function is e to the x, but the derivative is also e to the x. So if I go to this point 1 up here, then at the next value of 1, my function's e, but my derivative is also e. So that means that I know that this slope of this tangent line at x equals 1, the slope of this tangent line is e. And the slope of this tangent line is e squared. And when x is equal to 0, e to the 0 is 1. And so I know that this slope right here is 1. I know this slope is going to be 1 over e squared, etc. And so it's worth mentioning, I'll talk about this more when we get into the sections we need to cover in Chapter 6, but whenever you're doing any type of modeling with exponential functions, it's easiest to work in the base of e. And the reason for that is because of this relatively simple differentiation rule, is that the derivative of e to the x is e to the x. Okay, so let's look at all of our rules here. So let's do y equals e to the u, and I'm going to derive that for you. So if I have y is equal to e to the u, let's say I want to use the chain rule, then I'm going to use natural log differentiation again. So I take the natural log of both sides. U comes out. So I get the natural log of y is equal to u times the natural log of e. Natural log of e is 1. So natural log of y is equal to u. Differentiate both sides with respect to x. And I get 1 over y dy dx. And then here, be careful, because the derivative of u with respect to x is going to be du dx. And du dx we usually call u prime. So I get dy dx is equal to u prime times y. But y was e to the u in this case. So dy dx would be equal to u prime times e to the u. So that gives us the two major rules for differentiation of exponential functions. And so I'm just going to write those down. The derivative of e to the x is just e to the x. And the derivative of e to the u is going to be equal to u prime times e to the x. Or some people oops, not e to the x, e to the u. What you doing? All right, there you go. So that's going to be u prime times e to the u. And some people prefer to write it as e to the u times u prime, whichever you prefer. And so these are the two rules for differentiation, which are relatively simple. So let's do some examples. Okay, the first example is, let's say I have f of x is equal to 1 over e to the x squared, and I want to find f prime of x. Okay, now listen carefully, I'm going to write this down, is that you always want to get or work with, when you can, if you've got e to the, let's see, if I have 1 over e to the u, you always want to rewrite that as e to the negative u. Now, we didn't do this before, because remember when we had negative exponents, we'd usually bring them down. But we did do this, if you remember, using the power rule. Remember, like when you were first learning how to differentiate 1 over x squared, I would first rewrite it as x to the minus 2 and then differentiate. So I'm going to do the same thing with these e's. It's a lot easier to differentiate and to integrate this with the rules if you bring this up to the numerator. Okay, so I'm going to rewrite this function so it's easier to differentiate. And so I've got f of x is equal to e to the minus x squared. Okay, and then the rule that I want to use, remember, is that the derivative of e to the u is equal to u prime times e to the u. Okay, so in this case, I'm going to let u be equal to minus x squared. So be careful here, because this is e to the u, and that minus sign is in the u. And so my du then, or really my u prime is the way I want to write it, because I'm using the chain rule. My u prime is going to be minus 2x. Okay, so using this rule above, then I get f prime of x is equal to u prime times e to the u. And u prime is minus 2x, and e to the u is going to be e to the, and u is minus x squared. So this gives me my derivative for this function. Okay, let's do another example. Let's do y is equal to e to the tangent of x. Okay, so again, I'm going to use the differentiation rule. The derivative with respect to x of e to the u is u prime times e to the u. So in this case, I'm going to let u be equal to tangent of x, and du is equal to the derivative of tangent. And again, I did du. I should be doing u prime because we're differentiating. And u prime is equal to the derivative of tangent is secant squared of x. So then my rule then for the derivative is y prime is going to be equal to u prime, which is secant squared of x, times my e to the u, which is e to the tangent of x. And generally speaking, you want to put the exponential functions first because there's less ambiguity. So that's how I would write my final answer. Okay, next. Let's look at an example of finding points of extrema. Okay, so what we want to do here is we want to find the point or points of extrema on the graph of f of x is equal to x plus 1, quantity x plus 1 times e to the x. A couple notes here. Remember that points means both the x and y coordinates. And then the other thing is remember that e to the x cannot be equal to 0. And that will come into play momentarily. Okay, so even though we're dealing with e's, we use the same steps as before. So step 1, what we're going to do is take the derivative and look for type 1 and type 2 extrema. Now, before I take the derivative, well, actually, when I take the derivative, I could use the product rule and the chain rule simultaneously. It doesn't really make a difference, but I'm going to go ahead and use I'm just going to use the product rule of x plus 1 is u and v is e to the x. So I've got u is x plus 1, u prime is 1, v is e to the x, and then v prime, so the derivative of e to the x is just e to the x. So using the chain rule, I get the derivative f prime of x is going to be u prime v, so it's e to the x, plus uv prime, which is going to be x plus 1 times e to the x. Now, before I set this equal to 0, I'm going to go ahead and simplify this. So I'm going to multiply out this e to the x. So I've got f prime of x is equal to e to the x plus x e to the x plus e to the x. So I've got 2e to the x's. So f prime of x is going to be equal to 2e to the x plus xe to the x. And then I'm going to factor that out. So I've got e to the x times 2 plus x. Okay, so now I can find my critical points. And remember, to find my critical points, I'm going to set this equal to 0. Now here's the only thing that's a little tricky with exponential functions, is that normally when I set this equal to 0, I'm going to set both of these equal to 0. So 2 plus x is equal to 0 and solve for x, and then this term e to the x is equal to 0. But remember, and this is really important, e to the x cannot be equal to 0. E to the x cannot be equal to 0, and similarly, e to the u cannot be equal to 0. It's not inside the domain. So when I solve for this, I don't have to worry about this e to the x term because I know it can't be 0. So the only thing that's going to make this first derivative 0 is any of the terms that are not e to the x, which in this case is just the 2 plus x. So I get 2 plus x is equal to 0, and then that gives me x is equal to minus 2. And if I look at the domain of the function, the original function, it's going to be all real numbers. So therefore, I can declare this a critical point. So I've got a critical point, or critical number, I should say, at c equals minus 2. Okay, so step 2 is I'm going to check what type of extrema I have. And you can use the first or second derivative test. It's probably easiest to use the second derivative test. Well, I guess that's arguable, because here's my first derivative. But I'm going to use this form of the first derivative to take my second derivative. And so my second derivative, f double prime of x, is going to be, let's see, the derivative of 2e to the x is just going to be 2e to the x. And then the second one, I'm going to have to use the product rule. So it's going to be plus the derivative of the first, which is 1, times the second, plus the first times the derivative of the second. So here I've got 3e to the x, and I can factor out an e to the x. So f double prime of x is equal to 3e to the x plus xe to the x, or f double prime of x is equal to e to the x times 3 plus x. And remember, the second derivative test is looking at the second derivative at the critical point. So the second derivative when x is equal to minus 2 is going to be greater than 0. Because remember, e to the minus 2 is still positive. It's just 1 over e squared, so it's a positive number. And then, so I got positive number times 3 minus 2 is a positive number. So it's a positive number, so that's greater than 0. So that tells me that I've got a relative min. So therefore, c equals minus 2 is a relative min on the graph. And the last thing I need to do is find my points, because that's what's asked for. So in order to find my point, I'm going to plug my critical point, minus 2, into the original function. And so I get f of minus 2 is going to be equal to minus 2 plus 1 times e to the minus 2, which is equal to e to the minus 2, or is actually equal to negative e to the minus 2. So therefore, my answer is I've got a relative min at xy is equal to minus 2 comma minus e to the minus 2. Or if you prefer, you can write that as minus 2 comma minus 1 over e squared. Okay, so that's how you find extrema for these particular problems. Okay, so I'm going to push pause here because I'm already at the 17-minute level, and then I will catch you on the next video.